Okay, so welcome back. Hopefully you've seen the segment on limits. I'm now going to do colimits, which are going to be basically the same thing with the arrows pointing the other way. I'm going to do this somewhat more briefly because we've just seen limits. But I will give so I guess I could be very cheap and say a colimit is just a limit in the opposite category, but this is very unsatisfying. And really we want to be able to talk about diagrams of certain shapes. So I'm going to repeat some of these things. So this is colimits. So diagrams and shape categories are just as before. But when we come to define cones, things will get a bit different. So let C and I be categories, just as before, and let F from I to C be a diagram of shape I, which is just a really long-winded way of saying a functor. Okay, so then the key definition, and watch for the sort of subtle change, is a cone from F. Okay, so it's going to be basically the same thing, but with the arrows going the other way, is an object N of C together with maps, say psi I from F of I to N for all I in the objects of I. Okay, such that the usual triangles commute. So if I have, say, f of I, f of j, so this would be f of, I don't know, my map. So g goes from I to j, and then here I've got my n, and this is psi I, and this is psi j. Then I require that this triangle commutes. Okay, so it's just exactly the same definition as before, except that the arrows are now pointing from the f of I to the n instead of the other way around. Okay, we define a morphism of cones from F. Okay, I will not write out the definition again. It's basically just the same as before. So it's a morphism from, say, N to M, such that these triangles, such that all the triangles commute. So as analogously to before. To in the limit case. Okay, this gives us a category of cones from F, and then definition, the colimit of F, which we generally write as colim F, is an initial object in the category of cones from F. Okay, so definition looks very similar to what it did before, which is reassuring. So again, we could do some simple examples. So for example, if we have, to do our silly example, if we do the code, if I has a terminal object, then the colimit, the terminal object, say little I, the colimit of F is just F of I. So this is directly analogous to the case that we saw previously for limits. Maybe a more interesting example is that of coproducts. So if I is discrete, again, remember that being discrete means that the only morphisms are the identities. Then we call the colimit of F the coproduct of the F's of the objects of I. Okay, so for example, if, say, C equals a set, then coproduct is just the disjoint union. And this also works in a category of topological spaces. And then coproducts are just taking disjoint unions of things. Of course, in set, I mean take the disjoint union as sets, and in top, I mean take it with the usual topology. If you're not quite sure what the usual topology should be when I is infinite, then this is a good definition. Okay, so that's all very well. Let's quickly do, so we saw kernels and equalizers. Now let's do co-kernels and co-equalizers. Again, I should say here, I'm just asserting that it is in fact just the disjoint union. It's a really good idea to check this. Take the category of sets, take a discrete category with two objects, say, and construct a natural isomorphism between the disjoint union and the coproduct. Or show, maybe a better way to say this is, show that this disjoint union gives you in a natural way an initial object in the category of cones from F. So write down the maps and show that it is, write down the maps to make this thing a cone and show that it is initial. So, co-equalizers and co-kernels. So if I is again has two objects, we can call them 1 and 2, and we have two morphisms between them, say called A and B, then the colimit of this diagram I is called the co-equalizer. Oh, sorry, colimit, there must be always a diagram, right? So F is, as always, a diagram of shape I. Then the colimit of F is a co-equalizer of the maps F of A and F of B. So it's not, so notice that we took the same diagram as for equalizers. This is actually slightly unusual. Very often, if you have a diagram of shape I, then it will tend to be that either limits over it or co-limits over it tend to be sort of boring or silly things. But in this case, both the limit and the co-limit of a diagram of this shape are sort of genuinely useful things to study. So for example, if we take C to be the category of abelian groups, or equivalent, which is also known as the category of Z modules, and say F of B is equal to 0, then a good exercise is show that the co-kernel of F of A is the colimit of this diagram F. Again, here I'm abusing notation rather. The co-kernel you perhaps think of as just being a group, but you should really think of this as being a group together with a map from F of 2 to it, and therefore also a map from the zero map from F of 1 and the quotient map from F of 2. And then this thing becomes a cone, and then you want to check that this cone is initial in the category of all the cones from F. Okay, that's great. That's the end of this.